Привет всем, меня зовут Volker Simonis, я работаю в SAP, в отделе, который разрабатывает SAP JVM, это SAP JVM. Это виртуальная машина, она базирована на HotSpot Code от Oracle и от Sun. А что мы в SAP сделаем, это порт на много других платформах. У нас саппорт для HPUX, AAX, Itanium, PowerPC, Windows, Linux, Z-Architecture, ну и так далее. Хорошо, я сегодня вам расскажу по Packed Objects, Object Layout и Value Types. Ну, я расскажу по-английски, мне проще. А если хотите что-то спросить, можете по-русски. Я потом буду в экспертном зоне. Здесь сидит и Иван Крылов от Azul, он тоже работает с этим проектом, можете ему тоже спросить. So let's start with a short introduction. So what's the difference between value and reference semantics? In C++, we have both value and reference semantics. So let's take a look at this small example. If you have a class point, which has two int fields, x and y, and a class line, which a struct or class line, which aggregates 2 points, the layout of such a point, it's very easy. It's just the two fields. And the memory layout of a line class just aggregates the 4 integer fields of the point class. If we do an array of lines, it's the same. We have no overhead at all. All the fields are laid out, have a flat layout in memory. Okay, so in Java, the class point looks nearly the same. It has only basic types, integer. But already the class line, which aggregates 2 points, consists of 2 references, which reference the point objects. And these point objects, they can be somewhere else in the heap memory. Additionally, in Java, we have the problem that because Java has garbage collection, we need an additional object header, which describes the layout of the object, its size, which is used for locking and for other stuff in the virtual machine. So actually, even the simple point class has the overhead, the object header overhead, which is usually 2 words. The line class has 3 object headers and 2 references additionally. And when it comes to an array, we see that an array of lines has 2 references to line objects, and then again the line objects have reference to the point themselves. So what's the problem with this? Yes, first we have the memory overhead through the references and the object header. But today, CPU architectures, an even bigger problem is object locality. Because the members of an array, for example, they can be spread all over the heap. And if you want to traverse an array, this can bring us a big caching problems, because the objects won't be laid out in the cache. Also, to access an object in a line array, we have the so-called pointer chasing problem. So this means if we access the x coordinate of a point in a line array, this takes us 3 loads in Java, because we have to dereference 3 times the references before we get to the actual value, while in a C++ array, this is just one load. So today I will present some approaches how these problems can be solved. The first one is called Packed Objects, and it's by IBM. It's available in their Java-JDK 8 as a technology preview. IBM has worked on it since years, and they have published several papers and give several talks about this at Java 1, JVM Language Summit, and various other conferences. If you look at the slides, I have links to all these papers. So what they do is they try to completely remove not only the reference overhead, but also the overhead through the object headers. they create the object headers only on the fly if they are needed. And what they also support is access to native memory, so off-heap memory. This means we can allocate an array, for example, in native off-heap memory, which is very helpful if it comes to interoperability with native libraries, for example, with GPU or with other libraries. So the drawback of the approach, packed object approach by IBM, is that it's not Java anymore. It alters the semantics of a program. You have to enable it with the packed object option here, which is shown here in the last line. And finally, it's proprietary. It's only supported this way in the IBM JDK. So how does this look like? How do you program it? So in order to make an object being packed, you have to annotate it with the packed annotation first, and you have to derive it from packed objects base object. Also, the classes has to be final, and that's primarily all. So our point class would look like this. It has the packed annotation, it's final, and it extends the packed object base class. The line class has to use the packed annotation as well, and it has to specify that it uses other packed classes. So it uses the import packed annotation to declare that it will it uses packed points, and it also extends the packed object class. Then we declare the points like in the usual Java program, and in the library there is a helper class packed object which has a function which tells us if the packed object support is enabled or not. So if the packed object support is not enabled, I have just done this for a test program to show you what's the difference. We have to allocate the points. If we use the packed objects feature, then of course the points will be created with the default constructor, and we don't have to allocate them ourselves. Okay, there's another constructor which takes 2 points. Again, if you haven't enabled the packed object support, we can just assign the local fields with the points which we get in as arguments. But of course, if we use the packed object extension, we cannot simply assign a new object, because P1 is no reference in that case. It's just a value inside the line class. So we have to use the copy from helper function, which is declared in the packed object base class. That's why all the packed object classes have to derive from packed objects. So if we declare now, we have a test class, packed test, which creates new points. We can then create a line out of these points and print them to standard out. That's the usual Java semantics. If we now change the x and y values in the line object, this will of course also affect the point from which the line was created, because as I told you before, the line has just a reference to this point. But if you run with the packed objects enabled, you see that changing the x and y values of the line object has no impact on the original point object, because in the constructor we used the copy from form, which just initialized the point fields in the line object by value. The same applies the other way around. So if we change the x and y values of a point, this will affect the class in the case where we use the usual Java semantics, and it will not affect the line in the case where we use the packed object extension. Now, what happens if we assign the point field a new reference, a reference to a new object. Without the packed object, of course, we will get a line where the second point points to the one we assigned to. But with the packed objects extension, we will get an illegal access error, which says you cannot assign a nested field of a packed type. So this is actually how this works, and this is why I say it's not Java anymore, because there are certain things which cannot be done if you run with the packed objects extension. How do they implement arrays? Again, you have to extend the packed object base class, and then arrays are implemented as nested classes in the line class. So if you want to implement an array of lines, we have to declare a static final inner class in the line class, which extends, again, packed object. And this class implements the 4 methods I show here. So it's the allocate method, which calls the helper function from the packed array class and instantiates a new array with the element type being a line and with a specified length. Also, because we cannot directly use the bracket operator for array access, we have to declare a add operator and a get length operator, because we cannot just use the length field like in a native array. Again, using this is pretty simple. We can just define a new point, 2 new points, build a line, just like in the previous example, and we can now allocate an array of 4 lines in the following way, like we say line.array allocate 3, and this will give us an array of 4 line objects, and we can only access them with the add operator. We can assign them with copy from, or we can directly get a reference to a point, and in the point object, of course, we can assign the x and y values, because these are base types, it's integers. Okay, so to summarize the packed objects approach, again on the left side you see this is the usual Java reference semantics, and on the right side you see the approach IBM has taken. So what I want to say with this picture here is that they try to pack the line class very dense and omit the object pointers, the class, the object headers for the points. Only if we want to access a point, if we say line dot p1 and then want to put a lock, for example, on this object, then they will create an object header. Otherwise, that's not necessary for their VM and can be optimized. But of course, this requires special GC and support from the garbage collector, because the garbage collector nevertheless has to know the layout of the objects in the heap. Okay, this was the packed objects approach from IBM. Now I come to the second approach. It's called object layout. This was initiated by Jill Tene from Azul. And his approach is more to produce so-called layout optimized data structure, but in pure Java. So what he is doing is he implements a structure package which simulates value semantics in pure Java. And then the idea is that this Java library can be under the hood optimized by special VMs. I will show you how this will work. So again, on the left side we have the usual Java semantics. On the right side is the way how object layout is supposed to work. We have several approaches. For example, the approach, the implementation optimization done by Azul and Ivan so far, they, for example, don't optimize away the references. They still construct a line with 2 references to the point fields, but they align them near each other, so they still pack them dense. So this approach won't save you the memory occupied by the reference and the object headers, but it gives you a packed memory layout, which is still very helpful for performance reasons. And it also enables optimizations which completely eliminate the pointer chasing problem, because when you know that your fields are densely aligned behind inside your object, you don't have to dereference these references. You can just simply, like in C++, access every field with a fixed constant offset from the object address. I have done some experiments myself, and I took another approach. I eliminated the reference fields and packed the fields inside the line objects. Later on I will show you my implementation. So these are two different approaches. This approach is also simpler when people start to use, for example, reflection to change final fields, because as you will see, the Java library, the Java part is implemented in the way that it is intrinsified. In object layout speak, this is called these are intrinsified fields. These are implemented as final fields, private final fields. So usually a programmer cannot change these fields, but of course with reflection or unsafe, that's still possible. So if you use this approach, it's easier to de-optimize your compiled JIT code, for example, and fall back to the default Java semantics. While if you have this approach and somebody changes a field with reflection, I mean, there is no such field here, so something really bad will happen. So how does this look in Java? Again, I have a point class. In the point class, we don't have to change anything. It starts with the line class. If we want to lay out the points right inside the line class, we have to annotate them with the intrinsic annotation. And these fields, as I've told you before, they have to be private and final. And we use special helper functions to build these objects. So this is all implemented in Java, and it uses reflection to construct these points. But in an optimized version of the VM, these construction methods could be replaced by some VM magic to create the point classes right inside the line. Of course, the line has to be big enough. It has to reserve enough memory to hold this object. Again, I also have implemented a triangle class because I will use it later in my example. And this holds a line and a point. And the constructs within method takes the name of the field and the object, which is the containing object of the line. You could also use more complicated construction methods, which take a constructor as argument and which take more arguments. So you don't have to use the default constructor. Here the line will be constructed with the default constructor. You can also initialize the private final fields with the construct within method right in the constructor, but you can only assign it once. So again, this is just how to use it. And it's the same like with the packed object approach. You create points, you create a line out of points, and it has the usual behavior. So here I tried to line out the way how this is implemented in Java. So when you call the line constructor, it will, if you call construct within in the line constructor, it will call some internal helper method construct within, and finally it will come to the abstract intrinsic object model method construct element within. And this line, this method is the one which will be intrinsified into the VM. So this means in an optimized VM, this method won't call other Java methods like in the Java implementation, but instead it will just construct a new object in place in the containing object. So in the Java implementation, this construct element within, this uses reflection to construct a new point. It just takes the point constructor, calls new instance on this point constructor, and assigns the reference to the constructed object to the field. So as I told you, in the non-optimized version, we don't really have values. We have value semantics, but we still have references to the object. So the structured array example is a little more complicated. If we want to create a structured array of points, for example, we have to extend structured array, and we override the new instance method, which takes the length of the argument as an argument, and calls the structured array new instance method again with the first argument is the array class itself, so that's our class, structured array of points. The second argument is the element type, so that's point in this case, and then it gets the length argument. We can also create structured arrays, for example, without extended structured array. We can do something like this. Structured array of lines is just structured array new instance. Just say the element type, which is line, and the size. And then we can set the elements. The structured array class provides setter methods and getter methods. So the implementation of this is quite complicated. I can go through this in this talk, but if you look at the slides later on, this is the call stack, how a structured array of points gets created. So again, it uses reflection, and it has to use another trick, which is called constructor magic. So if we instantiate, if we call structured array of point new instance, we have to use thread local. We use a thread local object called constructor magic, which encapsulates all the arguments needed for the array construction, and then we call instance structured array, and we put another thread local constructor magic on the stack, and when we finally, through reflection, call the constructor of these classes, they can use the thread local constructor magic object to query, for example, the length of the array and the object type and the constructors we wanted to use. And with these information, finally the structured array will be created. And after we've created the structured array class, we call another yeah. So after we've created the array class itself, which allocated enough space for its elements, we now have to construct all the elements, and this again is done by using the Java lang reflect constructor of the element class, and unfortunately it doesn't work again. Maybe I speak too loud and the batteries are broken again, I don't know. So, by the way, again, in an optimized version of a Java virtual machine, these methods, these green methods will be optimized, and will provide the real the optimized layout. So what I have done is I have optimized the construct within method for the intrinsic annotation. It's available on GitHub in a Mercurial repository, in a Mercurial patch queue, which could be applied to the newest version of our OpenJDK source code. What I've done is I changed the class layout algorithm, so it accounts for embedded objects, which are annotated with intrinsic. I've intrinsified the construct element within method, so it doesn't create new objects, but constructs the element in place in the containing objects. I've fixed the interpreter so it properly handles get and put field bytecodes for the intrinsified fields. And I've done some optimizations in the C2 compiler to get rid of the data reckoning, the referencing. So there is a nice option called XX print field layout in a debug version of the Java hotspot. And if you run with this option, it will print you the layout of every object. So for a point class, it has just it has the object header, and then it has two fields which have type integer, x and y, and they have 4 bytes, and that's it. For a line class, again, it has the object header, and then it has the two fields p1 and p2, but these are references, so they also occupy just 4 bytes. If you look at, if you run with plus optimized object layout, which contains the optimizations I was just speaking about, we see that now the p1 field has place for 24 bytes. That's exactly the size of a point object. So it means when the VM now allocates a new line object, it will reserve enough place at P1 for P1 and P2 so that we can construct the point objects right inside the line class. And the same for triangle. It contains a line. It contains enough place, 64 bits, to hold the whole line object and the point. These are some implementation details. If you want to see how you can intrinsify a method in a Java VM, you can just look at it. I have no time to go through this. This is how the template interpreter works. You have to optimize. Of course, you have to be aware that you are not allowed to do any put field on intrinsified fields, because as I told you, they don't contain references anymore. They are just real objects. But because we aren't allowed anyway to use the put field on final fields, we can just ignore them in the interpreter, and get field, it's just even simpler than the usual get field in Java, which does a load from memory to get the real address of the object. We can just do a simple load with the intrinsified version. Also for the C2, what we can do now is instead of doing these several loads to come to the final address, we can just, the compiler already knows the offset of the x and y coordinates in a nested line or triangle class, and we can just go with one load. So if you have a program like this one, which takes a triangle and shifts this triangle, so it means it shifts every x and y coordinate by a certain amount of pixels, you will get for a line of code like this, triangle get line get point dot x, you will get in a usual Java VM you get 3 loads. Okay, so in an unoptimized Java VM, you will get 3 loads. First, you will load the line from the triangle. Then you will load the point from the line. And finally, you will add the x value to the x coordinate at the specified offset in the point object. Okay, with the optimizations I have done, this all collapses into one add command, which knows the offset. So, sorry. So 44 is actually the offset of the x coordinate of a point in a line. Actually, I wanted to show you this in a real demo, but I think we have not enough time. So I can show you this later in the expert zone, exactly. I will finally come to a third approach, which is called value types, value object as well. There are quite several names for the same thing. It's actually a proposal of John Rose and Brian Götz and Guy Steele. So what they are going for is they want to introduce real value types into the Java language, which is of course a huge change. This would feel like a real struct in C++, but this is a work in progress. It's just they wrote a position paper about a year ago and started working on this in the Valhalla project. So this is a Mercurial repository in the OpenJDK and the project, but it's still in very early stage, so there is no working code you can look at. But their approach is more general. So for example, with their approach you could also use value types for arguments, for return types, for locals, for array elements. But to achieve all this, you not only have to change the Java language, but also the Java virtual machine. So you probably need some new bytecodes, and you can imagine last time they introduced a new bytecode, how long that took. So it won't be for sure in Java 9, maybe in Java 8. Sorry, yes, 10, or even later. There was an earlier approach. It was the Java enhancement process 169 called value objects, but this just wanted to introduce a lock operation on objects, which makes objects immutable. But this was didn't got beyond draft stage, and it was merged in the value types for Java proposal. So to give you an idea, what they want to achieve is here's some bytecode from their proposal value types for Java, which uses new bytecodes. So all the V bytecodes are new. Let's just start with the usual way how we create a new object in Java. It's here on the lower right side. You say point p equals new point, and this is a new bytecode which allocates the memory space for the point in the heap. Then we duplicate it. We push the constants, the arguments of the constructor onto the stack, and we do an invoke special to the constructor, which initializes the point in the Java heap, right? So with their new approach, if you want to have a value class point, we annotate it by value. This is just syntactic sugar, probably this will change. It's just to have a common ground to speak about. So they annotate the class with the by value annotation, and then the point class doesn't have a constructor, which is called init in Java, but because it's a value class, they call it new. And also, this isn't doesn't have the L type for the class annotation, but they introduced a new one, Q, for value types, because V was already used for void, so they had to use some other letter. Okay, and now if you want to create a new point, you don't use the new keyword, because actually you don't want to create it on the heap. It's just a value object. It may live on the stack or in the registers or just somewhere. So you just say make value, you push the arguments of the constructor onto the stack, and then you invoke this new method, and this new method just does a vnew, which pushes the actual object. So this may be just the registers or just in the stack frame the space for the point. no difference how you optimize it. And then it initializes the fields of this value object with the vput field and does the vReturn. So that's the way how this could work in the future. So I have some more examples for nested values and an array example. So again, for the array example, if you create an array of points, you use the new vnew array bytecode, and then for all the points, there is already place. The vnew takes care that the array doesn't contain references to points, but it allocates enough space so we can now call the make value, the make value initialization routine on that place in memory. There are also various other projects currently underway which are related to object layout. There is the project Panama, which does the foreign function interface, for example. But it also, one of the goals is if you have a foreign function interface to call native functions, you also need a way. For example, if a native C function system call has an argument, a struct as an argument, you also need a way how to specify this in Java, or if it returns a struct. So they also care about native data access from within the VM, and also the array 2.0 approach also has some support for layout objects in memory. So if you're interested in this topic, there is a lot of reading. But it's all in the early stage, I would say. So actually, this was my presentation. If there are any questions,
Вопросы?
Да, работает. Я не думаю. Хорошо.
Why Azul implementation requires us to use some helper methods instead of replacing constructors at runtime or something like that?
You mean why you don't intrinsify the constructor?
Yeah, why we need explicitly use some helper methods to construct objects?
Because I mean it must work in Java, and and you have to optimize it. If you don't have this helper method, you still have the new bytecode. You have to somehow. You don't want to allocate in the heap. I mean the memory is. You have to distinguish between allocation and initialization, and that's why you need the helper methods. Because I mean the new bytecode it knows the length of an object, right? It's built into Java. And if you have something like a structured array of points, you cannot the new bytecode cannot construct types of different sizes. So one time you say I want a new structured array of 10 elements, another time of 20. So if you as I showed you before, if you just use new to allocate, it will be too late in the constructor. When you call the constructor, it will be too late to allocate more memory.
Yeah, but is it possible that I write code with constructor, but actually this code will be replaced to some other code without constructor, but this would be hidden from me?
I mean, you can call this construct within, for example, in your constructor, but the current implementation doesn't replace the constructor.
Yeah, so my question is it impossible in principle to make some such replacement, or it's just some choice?
I think it's not so easy, but we can discuss it later if you want. I can show you the implementation and we can discuss it later.
Okay, thanks.
I will be here all day. I'm happy to discuss it with you.
Еще вопросы? Можно на русском.
Thank you for your election. My question is, can you, I don't know, light or recommend development cases when we shouldn't use this approach, in your opinion? It's interesting. We discussed something about constructors, maybe some
You
cases.
mean where you don't want to use object layout or packed
Yes,
object?
yes. When we shouldn't, in your opinion, when you will not use.
I mean,
this
from a
approach.
practical point of view, you cannot use any of these approaches because they are just not ripe for use, for production use. And I mean, in the general case, I mean, you already have reference semantics, so everything which works now, it's fine. But there are a lot of libraries, for example, which use, for example, off-heap memory and unsafe to and do a lot of complicated stuff just to align to densely pack memory. And this is the case where you want to use it. So for example, you could imagine a new implementation of the string class, because now the string class, for example, it has a length field and a reference to the actual character array, right? So every time you access the character array, you have to do a dereferencing. If you have value types, you could just pack the character array right into the string, and you would save a dereference at every string operation. So that would save you a lot of time in, for example, XML processing, or the same with big integer or other classes which use structures of objects of the same type.
Вы вот описали несколько подходов, которые решают эту проблему упакованных объектов. Но проблема в том, что они частные и в виде экстеншена сделаны. Но проблема вообще-то серьезная. И стоит ли ожидать работы стандартизации Java для работы с упакованными объектами?
Но, как я сказал, они все не production ready. Это от IBM, они proprietary. А вот object layout, он в GitHub, можете ему пользоваться, но он не в Java стандарте, естественно.
Я как раз
А
и
вот
спрашиваю.
value object, он еще не готов. Там нужно еще подождать 3-4 года.
Но в данном случае все равно речь идет о каких-то расширениях Java, не встроенных в Java и не обещанные. Понимаете, что я имею в виду?
Давайте я отвечу чуть на этот вопрос. Object Layout собирается стать пропозалом на OpenJDK. И если вы знакомы с тем, как работают другие пропозалы в OpenJDK, то сначала появляется проект, он развивается в Open, потом, предположим, происходит голосование и решают, что мы согласны этот проект принять стандарт, скажем, Java 9 или стандарт Java 10, какой таймлайн. После того, как это решение принято, такая реализация, например, потенциально Object Layout становится частью стандарта. После этого все виртуальные машины, которые будут совместимы со стандартом, они все должны в том или ином виде поддерживать этот новый стандарт. Сейчас Object Layout в состоянии, вот мы собираемся создать OpenJDK проект. То есть он в начале пути, он должен пройти эту цепочку, и в конце концов мы надеемся станет стандартом Java 9 или Java 10, как повезет со временем.
Ага, спасибо. Но вы стараетесь, потому что это очень важно.
Вы сказали, что оно еще не production ready, но, возможно, вы уже где-то в каких-то решениях попробовали это использовать, и, может быть, у вас есть какие-то бенчмарки о том, типа, как там memory consumption уменьшился, или там код стал быстрее работать там в 10 раз. У вас есть какие-то такие примеры?
Только micro-benchmarks. Только micro-benchmarks я делаю, потому что как-то Object Layout, он еще не так 100% работает, что можно такие серьезные бенчмарки на него пользоваться.
Какие результаты этих микробенчмарков?
Ну вот это, с чем я вам сейчас покажу, он намного быстрее. Вот здесь я вам покажу, как выглядит функция, вот этот shift function, который я вам показал, да? Shift, да? Вот если не оптимизировать, вот у вас есть вот это ассемблер код, да, который JIT сделает C2. Вот это целая куча load, он сделает load point x, triangle, line, вот и так далее. А вы представляете, что вот если я сделаю оптимизацию, плюс optimize layout, и найдем shift, вот это все, что останется. Это только add, и все. Потому что JIT, он умный, он знает, что теперь все в одном месте лежит в память, и он может свободно с офсетом все сделать. Это, конечно, быстрее. И это только, что JIT не сделает load, а потом еще будет кэш, не будет кэш трэшинг anymore.
Насколько я понял, первых два аппроача, они делают как такой объект, куда помещают все поля. Ну, то есть что-то близко к тому, чтобы создать просто объект, например, line, это x1, y1, x2, y2, правильно? Вот. Ну, то есть с точки зрения кода мы получаем, как бы объекты остаются, но layout становится более memory optimized. Вопрос, как это выглядит все три аппроача для профайлинг тулов, то есть ну, смогу ли я видеть, сколько каких конкретно объектов, или там будут, возможно, какие-то проблемы. И второй вопрос, как garbage collection работает в каждом случае, ну, насколько он это все видит.
С тулами, я думаю, там не будет особой проблемы, потому что если VM знает, как все это оптимировать, все равно все тулы, они через JVM-TI поедут в VM, и это будет просто, это как escape analysis или все другие оптимизации, они тоже, если начинаешь профайл сделать или дебагинг, это надо все наоборот сделать, все оптимизации, потому что так не получится больше. А вот с лейаутом это не такая проблема, потому что просто VM знает, где лежит все в памяти. Я не думаю, проблема.
У меня, допустим, класс строка была линия, правильно?
Да.
У меня был класс линия, и я загружаю профайлер, я вижу, что у меня там столько-то класса линия лежит в памяти. Вот. А сейчас это будет вроде как, ну, не только... То есть,
да, но ты будешь видеть, что линия сейчас побольше. Вот я тебе показал, там ты видишь, что там на field layout, если ты без оптимизации едешь, там одна линия это 24 байтов, да, а если с оптимизацией одна линия это 44 байтов. Тебя меньше
поинтов я уже не увижу вообще.
Да, но зато lines они побольше. А по garbage collection лучше Иван спросишь потом.
Все, спасибо.
Я...